Early atomic theory. Dalton's model of the atom. Dalton's atomic theory resulted from the work done in chemistry during the 1700s. Several scientific laws were discovered during this time, which fed into Dalton's atomic theory. Most notably, the law of conservation of mass, the law of definite composition, and the law of multiple proportions. Dalton proposed that matter is composed of indestructible pieces, which he called atoms, from the Greek word atomos, which means indivisible. This is point number one. These pieces, atoms, combine together in specific amounts to form compounds. That's point number four. In order to explain the constant mass ratio of the compounds, Dalton proposed that the atoms of an element are identical, point two, and that atoms of different elements have different masses, point three. For Dalton, there were as many unique particles as there were different elements. Dalton's model results directly from his theory. Since atoms are indivisible and indestructible, they must be hard. Since we know nothing about any simpler particles than atoms, we assume the simplest possible form, which is that an atom is uniform and spherical. Thomson's model of the atom. While it took almost 100 years for a new model of the atom to be proposed, the proposal made significant changes in Dalton's model. We start with Millikan's experiment, the discovery of the electron. The existence of positive and negative charge had been known since the late 1700s, but Robert Millikan devised a very elegant experiment which determined that the negative charge occurred in distinct packets on a particle that was called an electron. In his experiment, he used an atomizer, a device which produced a very fine spray of droplets, to produce a bunch of very small droplets of oil. These droplets were allowed to fall into a space between two charged plates and were then hit with radiation that produced a negative charge on the droplets. Once he had the charged droplets, he looked for one that was stationary in midair. This particular droplet had two equal forces acting on it, gravity pulling down and the electric force pulling up. The electric force is dependent on the charge on the droplet and the electric field produced by the charged plates, which can be determined from the charge on the plates, which we can easily measure. The gravitational force is determined by the mass of the droplet and the gravitational constant g, which is well known. We could determine the charge on the droplet if we knew the mass of the droplet. To determine the mass of the droplet, Millikan simply shut off the electric field. The droplet began to fall, but quickly reached a constant speed because the air resistance acts in the opposite direction of the motion. The speed reached depends on the surface area of the drop. If we assume the drop is spherical, then the surface area is related to the volume of the drop. From the volume of the drop and the density of the oil, we can get the mass of the drop, and then we can calculate the charge on the drop. Millikan found many different values for the charge on the drop in the thousands of experiments he did, each of which can be done in less time than it takes to describe it. However, he found that these values were whole number multiples of the smallest charge, which he described as the electron. J. Thomson performed some experiments with a cathode ray tube. This is a picture of his actual apparatus. The tube has a cathode, which is a metal electrode that produces the cathode rays, an anode with a hole in it through which the cathode rays pass, an electromagnet, and a pair of charged plates. Here is a schematic which helps us to explain what's going on. The cathode rays are really particles that carry a negative charge. When these particles pass through the hole in the anode and continue on with no magnet or charge on the plates, they pass through and strike the front of the cathode ray tube, which is coated with zinc sulfide. Zinc sulfide glows when a charged particle hits it. A bright spot appears at B. If only the charged plates are turned on, the spot moves to C. If only the magnet is turned on, it appears at A. The shift is due to the fact that a force is being applied to the particles as they move between the plates or the poles of the magnet. Thomson turned on both the plates and the magnet and adjusted things so that the spot once again appeared at B. In this way, the particles were being acted on by two equal forces, an electric force from the plates and a magnetic force from the magnet. Because of the nature of the electric field formed by the plates, the electric force only acts on the particle while it is between the two plates. Similarly, the magnetic force only acts while the particle is between the poles of the magnet. The amount of deflection caused by the electric force depends on four things: the strength of the electric field, the charge on the particle, the mass of the particle, and the speed of the particle. The charge of the particle and the strength of the field produce the electric force on the particle. The greater the mass of the particle, the less acceleration is produced by the force, and the less deflection occurs. And the faster the particle goes, the less time the force acts, producing less deflection. Similarly, the deflection caused by the magnet depends on four things: the strength of the magnet, the charge on the particle, the mass of the particle, and the speed of the particle. The strength of the magnet and the charge on the particle produce the magnetic force, and the mass and the speed affect things the same way they did with the electric force. We can easily measure the strength of the electric field and the strength of the magnet, but we cannot measure the charge on the particle, the mass of the particle, or the speed of the particle, all of which influence the deflection. However, when we combine the magnetic field and the electric field from the plates so that the forces are equal, the speed of the particle becomes irrelevant, and we are left with a mathematical relationship that involves the charge-to-mass ratio of the particle, Q/m. If one tries different metals for the cathode, the same charge-to-mass ratio is produced, which strongly suggests that we are getting the same particle, the electron. The electron has a very large charge-to-mass ratio. It is possible to reverse the poles and get positive particles if one places a gas in the tube. The negative electrons are removed from the gas and positive particles result. However, we get different particles with different gases. The largest charge-to-mass ratio is found for hydrogen, which is the element that has the smallest mass. This mass is the mass of the proton. If we use the charge discovered by Millikan and the charge-to-mass ratio found by Thomson, we find the mass of the proton is about 2,000 times the mass of the electron, and is about the same as the mass of a hydrogen atom. This leads to Thomson's model, which has a positive atom with negative electrons embedded within it, spread out evenly. Thomson called it the plum pudding model. For us, a clearer image is the chocolate chip cookie model, where the cookie part is the positive atom and the negative electrons are the chocolate chips. The atom is still spherical. Ruteherford's model. Ernest Ruteherford and his research group used alpha particles, a type of radioactivity, to investigate the inner structure of the atom. The alpha particles are positively charged and rather massive, having twice the charge of a proton and 4 times its mass. The idea was that these heavy particles would interact with the protons in the atom, and how they interacted would reveal something about the arrangement of the protons in the atom. The experiment, called the alpha scattering experiment or the gold foil experiment, consisted of a very thin piece of gold foil, chosen because it was a heavy atom with lots of protons and because you could make a really thin foil out of it. A beam of alpha particles was directed through the piece of gold foil. The particles were then detected by a screen, initially placed only in front of the gold foil. It was expected that not much change could be found for the particles. They were much heavier than protons, so, like a softball rolled through a bunch of tennis balls, it was the tennis balls that would be expected to move. There would be some effect on the alpha particles, but not much. Initially, Ruteherford found virtually no deflections at all, less than he had expected. When the detector was extended around the gold foil more completely, however, an experiment actually done by Geiger and Marsden, other members of the group, large deflections were discovered, and even some reflections. This was totally unexpected. Ruteherford commented, "It was as if I had fired a cannon at a piece of tissue paper and the shell had bounced back and hit me." In order for the alpha particles to be deflected through large angles, there had to be a lot of force applied, and that meant that there needed to be a concentration of positive charge in the atom. In order for the alpha particle to be reflected, there needed to be something much more massive than the alpha particle that it hit. A bowling ball does not bounce off a tennis ball, but a tennis ball does bounce off a bowling ball. This is the nucleus. The nucleus holds all of the positive charge and most of the mass of the atom. As was discovered later, the nucleus contains protons and neutrons and is extremely small, 1/10,000th of the radius of the atom. So Rutherford's model of the atom has a nucleus which contains the protons and neutrons, all the positive charge, and most of the mass. And the electrons take up most of the space of the atom. Note that this picture does not show the relative sizes of the nucleus and the atom to scale. This arrangement is closer to reality, although it still shows a nucleus that is much larger than reality. This table shows the relative charges and masses of the 3 subatomic particles. Protons and electrons are the only particles that have a charge. Protons and neutrons have essentially the same mass, although not exactly so. The mass of the electron is so small that we can ignore it.